Good morning, good afternoon, wherever you are in the world. Welcome to the Romax Technology Introduction to Whine Problems and Solutions webinar. Thank you for joining. I'm Rohini Sayal, Romax Marketing Campaign Manager, and our presenter today is Dr. Michael Platten, Noise and Vibration Specialist, Product Manager for Dynamics at Romax Technology. The presentation today will last approximately 40 minutes with a 10-minute Q&A session. So let's get started. I'll now hand over to Michael and let him give a full overview of the webinar.
Thank you very much, Rohini. Welcome everybody to this webinar. It's great to see so many people attending, and I hope you find it interesting. This webinar is the first in a series related to NVH and driveline systems, and the overall aim of this webinar series is to show you how to design and evaluate NVH characteristics throughout the design cycle, from early development through to final design, allowing you to solve NVH issues earlier on in the process and therefore streamline your processes to make them faster. We're going to be looking at diagnosing, over the course of the next three or four webinars, we're going to be looking at diagnosing and solving gear whine problems. We're going to be looking at some particular examples, some detailed case studies about looking at gear whine noise problems in various situations. That will be in the next webinar. And then another webinar on the specifics of gear whine analysis in planetary gears, which is somewhat different to other types of gear. And all of this is with the aim of reducing costs for prototyping, reducing development time, giving you higher quality designs faster using a right first time approach. So part one of this series is today, and that's an overview of gear whine theory and an introduction to solving and preventing problems and methods you can use to do that. Part two, which is on the 7th of July, we'll look at some in-depth case studies, as I said. Part three, we'll look at the planetary gears, and then part four, which will be at a time yet to be decided, we'll be looking at NVH in electromechanical powertrains, and that's including noise coming from electric machines such as motors, as well as from gears. So today we're doing the introduction, and here's what we're going to be talking about. We'll have a brief introduction, and I mean brief because it is a very big topic, but just to give you a flavour of what gear whine theory is, what the causes and effects of gear whine are. We're going to look at how we can simulate gear whine behaviour, and we're going to look at some hints and tips, if you like, on how to prevent gear whine problems, both in terms of things you need to consider and things you need to simulate. And then we'll finish off with a demonstration of simulating gear whine using Romax Designer. So what is gear whine? Gear whine is a tonal noise, i.e. it's a sinusoidal type noise, which stands out against the broad background noise. So, for example, in a car, broad background noise would be things like wind and tyre noise, and tonal noise would come from the transmission and the engine, and they stand out against these backgrounds, and people become aware of them, or they cause a generally annoyance and a noise problem. It is an annoyance rather than anything more serious. It's a quality issue. Gear whine never really caused anything to fail. I've never heard of anything where that happens. So it's very much a quality issue, but that doesn't make it any less important, because of course that affects the ultimate quality perception of a product. And there may be legislation as well that means you have to have particular noise levels. Gear whine is caused by imperfect transfer of motion in gears, which we call transmission error, and that's what I'm going to talk about in just a second. But it's also important to understand that gear whine is not just about gears, it's actually about the whole transmission and driveline system. Because although the gears, as we'll see, is the source of the noise, the whole system actually plays a role in that process, and we need to be considering the whole system throughout our design and analysis and simulation of this process. So the cause of transmission, the ultimate source of transmission, of gear whine, is transmission error. And what do we mean by transmission error? So as I mentioned just now, transmission error is caused by imperfect transfer of motion by gears. So if you look at this graph here showing the speed of a gear versus time, you can see for an ideal gear, a perfect gear if you like, we would see if the driving gear was moving at a constant speed, the driven gear would also move at a constant speed, determined by the ratio. However, when we have real gears, we don't have perfect transfer of motion. And so even if the driving gear is moving at a constant speed, then there will be fluctuation in the speed of the driven gear. So this results in a displacement at the gear mesh, a varying displacement which varies each time the tooth goes through the gear mesh. And that is what we call the transmission error. And this excitation that the transmission error causes leads to vibrations in the system transferred through the system, which can be radiated as noise or as transferred as vibration to other parts of the structure. So what causes transmission error? We know transmission error causes gear whine, but what causes transmission error? We've said that if we had perfect gears, we would have no transmission error, but we don't have perfect gears. If they were true involute gears, perfectly manufactured, perfectly aligned, perfectly rigid, then we wouldn't have TE. But in the real world, real gearboxes don't have perfectly rigid gears. The gear teeth deflect under load, they bend and they deform. The tooth surface itself deforms under high contact load, which causes the shape of the gear to change. And also, real gearboxes don't have perfectly aligned gears. The picture here shows an exaggerated transmission, the deflection of a transmission that's deflected under load, and you can see there are components are moving, and therefore we get a degree of misalignment. We have flexible shafts in a transmission or in a powertrain. The housing obviously is not perfectly rigid, and things like bearings have clearances, all of which add up to produce misalignment in the gears. Also, gearboxes have tolerances in the mounting and alignment and manufacture of components, and again, these all add up to cause additional misalignment. Also, in the real world, gears do not have true involute profiles. In fact, we deliberately design gears with modifications that we call microgeometry to make them not true involutes. And in fact, these are there partly to improve the NVH performance, as well as the durability performance. And of course, even whatever we design, when we come to manufacture it, there will be variability. Depending on the quality of the manufacturing and the desired quality of the gears, the variability may be high, it may be low, but we also need to consider that as part of the process. And then in the end, all of these effects combine, so the static deflections, the flexibility of the gear teeth, the manufacturing variability, and the design of the gear all combine to affect the way the gears behave when they come into contact. You can see an example of a contact load distribution here on a gear pair, and that in turn affects what the transmission error is. So we have to consider all of these things in the calculation of the transmission error. So already you can see it's not just about the gears, because we have to consider the deflection of the system as a whole in order to be able to properly understand transmission error. So once the transmission error is there, what happens next? What are the effects of transmission error? So the transmission error causes a excitation at the gear mesh, effectively, which is then transferred through the components, through the shafts, through the bearings, to the housing, and the whole system responds in vibration and resonance, and ultimately leading to noise radiation. Predominantly when we're talking about gear whine, we're talking about two or more specific failure modes, and that is vibration that is transmitted from the gearbox through the mounts and through the shafts, and noise that is directly radiated from the housing of the transmission. When we think about noise control, the model that people usually talk about in general, not just for gear whine, but for noise control, is what's called a source path receiver model, and it's a way of helping us to understand how to tackle noise problems such as gear whine. So the source is the ultimate generator of the noise. In our case, that's our transmission error. The path is the means by which the noise gets from the source where it's causing a problem, and the receiver is the place where the noise is a problem. And we can tackle noise problems by trying to improve each of these things, the source, path, and the receiver. But in most cases, we're almost always trying to reduce the noise at source, as that is usually the best approach. But that may not always be practical, so we do need to consider the other things as well, by making changes to how the vibration is transmitted, i.e. the path, and also remedial noise treatment in terms of protecting the receiver in a car that might be the driver or the passenger in the passenger compartment. So for a gearbox, the source path receiver model is quite straightforward. So our source, as we say, is the vibration excitation at the gear mesh, which comes from transmission error, which is transmitted through the gears and the bearings under the gears, through the shafts and through the main bearings into the housing, where it can then be radiated as noise, for example, or excite vibration through mounts to other parts of the structure, or through the input and output shafts. We can think of a source path receiver on another level as well. We can think of it within the complete system, if you like, in the illustration here by a car. And in this case, we can consider the gearbox as a source and the receiver as the driver, and the paths in between are a direct radiated noise path, airborne path, and then various structural paths through the chassis, which then re-radiate noise. I'm using cars as an example here, but it applies to any kind of structure like this. In this case, then, one of the common ways of dealing with problems is looking at the path, and we might look at the vibration mounts. We might look at putting additional noise treatment between the engine and the passenger compartment, for example. But again, the ideal approach is to look at reducing the noise at source. So that's a very brief overview of what Whine is. We're now going to look at how we can simulate it. So we need to be able to simulate Whine for a number of reasons, but the main things being we want to be able to predict the behavior of our system at the design stage to see if it meets the required performance targets for noise. And usually, first time you design something, it's not going to meet the targets when you analyze it. So we need to be able to also have the tools to help us redesign and optimize the design to meet the targets. We can, in the same way, we can also use it to troubleshoot existing Whine problems and identify potential solutions. But the ideal scenario is that we've ironed out the problems before we get to the phase of having a problem in actual production conditions, which is why we call it a right first time design process. In simulating Whine, we need to consider a number of things. We've already said we need to consider the whole transmission and driveline system, not just the gears. Obviously the gears are the source, but we need to consider the rest of it because they're heavily involved, including how the gears are misaligned. Obviously depends on the rest of the system. We need to be able to simulate how the gears contact, how the vibration is transferred to the housing and to the outside world via vibrations and radiated noise. And also critically, we'll see later, we need to be able to understand the variability, because although we design a nominal transmission, of course there are tolerances, of course there is manufacturing variability, and we need to understand the sensitivity of our design to those variabilities. So to illustrate this point, I'm going to introduce the concept of the Whine chain, and this shows how each is on another thing, and therefore that we need to consider all of these things if the chain is not to be broken. So, for example, we know that the gear and bearing misalignment, we've already talked about this, depends on the static deflection of the whole system under load. So we need to model the whole system, we need to model the static deflection of the whole system to obtain this. As we saw at the start as well, the transmission error and also the bearing stiffness, which plays an important role in the transfer of vibration to the housing, they depend on what the gear and bearing misalignments are. So again, we need to know what the misalignment is to understand that. And then similarly, we need to be able to simulate the dynamic behavior, obviously, and that depends on the transmission error and the bearing stiffness. And finally, if we want to look at the result, we actually want to look at its vibration and radiation, and those things obviously depend on the dynamic behavior. So unless we include all of these things, the chain is going to be broken and we're not going to be predicting the right thing. So here's an overview of the Whine simulation process, and we'll run through this when we look at the demo. But there's a number of steps, all of which happen, which rely on the previous step. So the first thing, obviously, if we need to model the whole system, then we need to build a model of the whole system, and that as well as including the system, obviously includes the realistic boundary conditions in which the system is situated. We need to make sure that environment is correctly modelled so that we are representing a realistic situation. When we have our model, then we want to look at the static deflection of the transmission under load, which in turn gives us our misalignments. Once we have the misalignments, we can analyze the contact behavior of the misaligned gear under load, and from that we calculate the transmission error, which is our excitation. But now we need to have that dynamic model to which we can apply the transmission error. That is usually done using a linear frequency domain model. That's gives us accurate enough results, as you'll see later, but also is very, very fast to run, which is important when we come to look at things like variability and sensitivity analysis. Once we have that model, we can apply our transmission error in the form of an excitation to that model, and from that we calculate the vibration response, and ultimately we can then calculate radiated noise from the vibration response. Obviously this needs to be accurate to work, and I've just put two examples here on the screen of demonstrating that this process does actually give correlation to tests. These are two examples from our customers. We have many more examples than this, but typically customers don't allow us to show them, but these two have been published in papers. The one on the top here with Renault, and you can see a good correlation here. This is in terms of housing vibration measured with an accelerometer. And very recently, just 2 weeks ago, I presented this result in a conference in the USA, which is based on a Ford automatic transmission. And here we're looking at radiated noise in a very complicated transmission, including the effects of manufacturing variability. But again, we still get very good correlation, even though it's such a complex process and also a very complex system. So we'll see. We'll run through the simulation process again when we look at the demo. But now I'm going to talk about preventing gear whine problems, how we design transmissions to be quiet from the start. I'm going to introduce you to the concept of right first time. Some people call it CAE-led design. And then I'm going to go through some guidelines for low noise design of transmissions. Now, again, this is a relatively short webinar, so we can't go into huge details, but there's some real useful nuggets of information here about how to start off with a good design, i.e. give you the best chance of getting a quiet design, and then look at the things that you need to consider in terms of design and optimization. And very importantly, we're also going to look at the fact that we need to consider other design targets when we're talking about noise and vibration as well, and look at the requirements for optimization of the complete system and variability analysis to examine the effect of tolerances and sensitivity to them. So what do we mean by right first time? Well, if you consider a classical development process, you have a design stage, then there is a verification stage, typically using CAE tools, which then requires some redesigns and re-verifications and so on, before moving into a prototyping phase and moving forward to manufacture. And at each stage, the design confidence increases as we progress through these phases, but actually the design confidence is not that high until we reach very late on in the process. When we talk about a right first time process, i.e. where we are using simulation to lead the design, we have multiple iterations of simulation within the design. We have tools that allow you to look at simulation in our case, NVH, very, very early on in the process, as well as at the detailed level. And we can repeatedly do these analyses during the process because they run very fast and they're very easy to run. And the upshot of this is that we end up with a higher design confidence much earlier in the process, and also the whole process is considerably shortened because the troubleshooting phase is greatly reduced. The idea is that we've ironed out as many of the problems as we possibly can during the early phases, by simulation, and therefore we're not left with any nasty surprises when it comes to the prototyping phase. This slide summarizes what I've just said, we're using CAE simulation to lead the design process. We need to do it multiple times during that process, from concept to the detailed level, to make sure at each stage we're avoiding these nasty surprises before prototyping. Because it's much easier to make design changes earlier on than it is once you've got to the prototyping phase, and have much more of an impact in terms of improving noise performance. Of course, in the early stages of the design, we're not going to be getting brilliant correlations like I showed you on the a couple of slides ago. We don't have enough information early on to be able to do that, but there are guidelines and tools and methods that we can use to understand the NVH early on, even if it's just comparing one design with another and giving us design direction information, qualitative directional information. That, as I say, the aim is to give ourselves, at each stage of the process, give ourselves the best chance of producing a quiet design. So we're going to talk now about some guidelines for reduced gear whine noise and designing quiet transmissions. As I said, this really is just an overview, but this should give you some really useful little tips to consider. And of course, the first thing is that we know some key properties of design that are affecting the NVH performance are some of those things that we have to define right at the very beginning, even to get down to things like tooth numbers on gears and module and types of bearing and that kind of thing. So for that reason, it's very important that you consider NVH and gear whine right from the very start, because that is when the biggest impacts can be made. We're going to look at the design layout for minimizing misalignment variation with load, and I'll explain why that's important in just a second. And then we'll look at specifics about design considerations for gears for low transmission error. And then we'll look at optimizing the housing for reduced vibration and radiation, i.e. addressing the path and the receiver part in our source path receiver model. And then we'll look at managing tolerances. So I mentioned misalignment variation. Now, misalignment in itself does not cause gear whine, but we know transmission error is affected by misalignment. And in fact, it turns out that it's a lot easier to design gears with low transmission error if we don't have to cope with a wide range of misalignments. So when a gear goes from, for example, very high reverse loads through very light loads through to very high driving loads, the misalignment will change as we do that. But what we don't want to have is the very wide range of misalignments in that spectrum of loads, because we have to be more aggressive with our microgeometry design, and that tends to lead to higher transmission error, or at least not being able to optimize the transmission error across a wide range of those torques. How can we address misalignment variation? Well, obviously the things that affect misalignment variation are things that affect the static deflection of the gears. And so we're talking about optimizing the layout of the transmission, investigating changing bearing stiffnesses by, for example, looking at clearances and preloads and bearing types, the stiffnesses of shafts and how they deflect, where the gears are positioned on the shafts, and therefore how the gears deflect, and also the stiffness of the housing itself, which obviously deforms as well. With gear design and optimization, obviously this is us trying to reduce the noise at source. We're trying to minimize transmission error. There are a lot of things that have an effect and a lot of things that you can do to help ensure quiet designs. So in general, for example, when we look at the gear, the coarse gear details, the macro geometry, we're looking for things like hunting ratios, where we want to avoid having ratios which are have low common multiples of gear teeth. So for example, if you don't want to have a gear with, if you can avoid it, you don't want to have a gear with, say, 50 teeth on one gear and 25 on the other, because when there are errors on those gears, those same pairs of teeth will come around in contact time after time after time, every 2 revolutions, in that example, and that is likely to lead to potential problems. Similarly, we want to avoid having gear sets, if we have multiple gear sets in the system, that have similar tooth meshing frequencies. We don't want them to be overlying, because they might add up. Okay, they might cancel out, but more than likely they will add up in some way. And also we don't want to have gears where the meshing frequencies are close to each other, because that affects the noise quality. It can lead to sort of beating effects, which are even more annoying than ordinary gear whine, if you like. Now, the best thing that you can do to reduce transmission error is design gears with large contact ratios, whether that's axial or transverse contact ratio, and that is the basis for a low TE design. Now, obviously, you're constrained by space. You may be constrained by the modules that you can use and the helix angles that you can use, which affect the contact ratio. But you want to be aiming for as large as you can get in a particular situation. And in particular, even though bigger is better in terms of contact ratio, but in particular, we want to be looking for a contact ratio which is around the integer, a whole number. In fact, ideally just over. So we're talking the contact ratio is 2.1, that kind of thing. We don't have time to go into the reasons for that now, but those give you the best conditions for low transmission error, and they're also the most robust in terms of their sensitivity to variability in the parameters. So that's the macro geometry. On the micro geometry side, we want to be optimizing the microgeometry to reduce the transmission error across a range of loads. So for that, we need to be using computer tools. It's not something you can really do, except for spur gears. It's not something you can really do with rules of thumb. You need to have the contact analysis involved there. And as we said before, it needs to include these misalignment effects if we want to get accurate contact behavior. We want to be ensuring that the transmission error is not just low at one load, but typically machines with gears in are subject to a range of loads, and we want the TE to be low across a range of operating conditions. Typically, that's not possible to have it low at every single loading condition, and at some point it will increase. But usually we want to concentrate on the lower loads, because if you think of, for example, in a car at lower loads, talking about lower road speeds or low acceleration levels, low vehicle acceleration, where we don't have lots of engine noise to mask, and we don't have lots of wind, road and tyre noise to mask it. That won't be true in every situation, but typically we concentrate on optimizing the low loads while still making sure that the higher loads are not too noisy. We also want to design the microgeometry so that we get contact over a large area of the tooth. And this is related to the misalignment, managing the misalignment variation, because if we have a large misalignment variation, we have to put a lot of crowning on our teeth to compensate for that. And if we do that, then we end up with a smaller contact area. And remember, contact area and contact ratio is critical in getting a low transmission error design. And finally, we need to analyse the sensitivity of the design to variations in manufacturing. We can't just consider the nominal. We want a design that's robust and that gives us low noise across a range of tolerances. Obviously, there we have to specify tolerances. We want to make sure that our design is not only optimised for the nominal condition, but also works elsewhere in the tolerance bands. In terms of housing vibration and radiation, in general, we want to avoid large unstiffened areas on the housing that are going to resonate a lot, essentially acting as loudspeakers. They have a very large potential for radiation, and we can simulate that behavior, as we'll see shortly. We obviously want to simulate the vibration to identify those problem areas, and based on the results of that simulation, we can look at adding in additional stiffeners, ribs and so on the housing where necessary to help improve the vibration. I mentioned this before, but you need to make sure that you include the boundary conditions for the transmission and driveline in the simulations, so that we get good predictions, because one of the things we're interested in, of course, is vibration at the mounts, because that is what transfers vibration to the rest of the structure. And therefore we need to have a representation of how the transmission is mounted in our model. Now, it depends on what you're trying to model. If you're trying to model a test rig, for example, then the mounting conditions and the boundary conditions will be different from if you're trying to model a sort of more realistic scenario of the gearbox and driveline in operation. but whatever it is, we want to make sure we're modeling what we're testing and testing what we're modeling. You can also use FE-based optimization tools like OptiStruct to help minimize vibration as well, in conjunction with software like Romax Designer. And of course, one of the targets is for these things is typically radiated noise. So we can use the output of our vibration analysis as an input into acoustic radiation simulation to check the radiated noise target. I've mentioned several times about tolerance and design robustness, and I mentioned this earlier in terms of gears, but also in terms of the whole system. We need to understand the sensitivity of the whole system to manufacturing and assembly variability. We'll see a little bit more about this when we talk about planetary gears in the third webinar in this series. We need to be able to simulate variability, and that usually involves running multiple simulations with small variations to the model each time. And therefore, we need to have a fast simulation tool to be able to do that, so we can look at those scenarios and gather information about sensitivity to tolerance variation. And as a result of this, you may find that you actually have to tighten tolerances on particularly sensitive parameters, or look to change the design to reduce sensitivity. And of course, those things add additional cost, but to a design. But your tool will provide you with the information that you need to be able to do that, and to weigh up those decisions and to make those decisions. And on that note, I'd like to especially reinforce this point, which is that we need to consider other design targets as well as NVH. Gear noise is not exist in isolation from other design targets. All these things interact with each other: the noise, the durability, the efficiency, the cost, and the manufacturing. And although I hate to say this because I'm an NVH guy, but NVH is nowhere near the most important of those things. If it breaks because of durability problems, then it's no good. If you can't manufacture it, it's no good. Remember, NVH, in terms of gear whine, is a quality problem rather than related to durability. But also we have an effect on efficiency, and also the choices we make, as I've just said, have an effect on the cost as well. So if we make a design change to improve NVH, we need to make sure it's not affecting the durability, manufacturability, cost, or efficiency, or any other design parameter. And so when it comes to optimization, we're talking about a balancing act between each of those performance targets. And what this means is that whatever we're doing in terms of simulation, we must be able to simulate all of these things simultaneously. So we make a change to the design to improve the NVH, we assess the NVH, but we also assess its changing effect on those other design targets as well, if we want to have a good design. I'm going to move on now to have a look at demonstrate this process on for gear whine simulation. When we've done that, we'll come back for a quick summary, and then we'll have the question and answer session. So what we're going to look at is a model of a manual transmission. It's one of our example files with Romax Designer. You can see the model here. It has a housing represented by an FE mesh, so we're accounting for the housing flexibility. Underneath we have 5 speed gears and a final drive gear, and we're going to be looking particularly at the final drive gear, but we will look at some of the other gears as well. And if you remember, the first thing on our list that we needed to be able to do was to simulate the static deflection behavior under various loading conditions to determine the misalignment. So I'm going to set this off running an analysis which is going to report to us the gear mesh misalignment for each of the loads that are defined in this particular model, and then we'll look at how they vary. So what is happening now is that it's running the static deflection analysis on the whole transmission, including the flexibility of all those components under different loading conditions. In fact, here we're looking at one loading condition in each of the 5 gear states of this transmission. When it's run that analysis, it should bring up a table showing us what the misalignments are in each gear. Just make this a little bigger so you can see it. So we're interested in this table here. So we've got different load cases for each speed condition: first, second, third, fourth, and fifth, and each of the gears down here. We're interested in the items highlighted in green because these are the gear meshes that are under load. So in first gear is engaged, and the final drive gear is running. Second gear is engaged and the final drive gear is running, and so on. So we talked about misalignment variation, and here you can see for each of these loading conditions, you can see the misalignment and how it changes when we move from first speed through to fifth speed. And that's partly because of changes in torque, but also partly changes in terms of which gear is engaged elsewhere, and therefore the forces that imposes on the gearbox and how it therefore deflects. In this case, we're going from a misalignment of about -5 microns up to a misalignment of about 24 microns. Now that's a relatively small range of misalignment variation. I've seen better, I've also seen a lot worse. So we would like to think that we'll be able to optimize this design across this loading condition without too much problem, without having to put too much microgeometry modification in place, and therefore gives the best chance of having a low TE right across the range of loads that this final drive gear is experiencing. So now we understand the misalignment, we need to look at getting the transmission error and doing the contact analysis. So I'm going to look at the final drive gear, look at the fifth speed low case, and in this chart you can see how the microgeometry has been defined on this gear. So this shows the modifications that have been applied to the teeth on this gear, and it's a mixture of lead slope and crowning with some tip relief as well. So that's going to affect our contact behavior. So we've got the misalignment, we've got our microgeometry, we know what the loads are. Those are the things that we need to input into our contact analysis. So we can run the contact analysis for this example, which doesn't take very long at all. Obviously we would run this for several different all the different load cases ultimately to understand what's going on in each case. And what appears is the transmission error here. This is showing the transmission error and how it varies over one meshing cycle, how one tooth going through the mesh. And you can see in this case it's approximately sinusoidal, not quite, and you can see it varies from about 14.9 here up to about 15.8. So we would call that approximately, we can find out exactly in a second, but that's going to be around about 0.5 microns of transmission error, because we talk about the amplitude of a transmission error. I can look at the Fourier transform of that, which will tell us for certain. And indeed, it's actually slightly less than what I said. It's around about 0.4 microns here for the first harmonic of transmission error. Other harmonics do exist. They're much smaller, but they can still have an influence. The contact behavior of this gear, we've got contact here. It's away from the edge of the tooth, which is a reasonable contact. It's in a pretty small area. That's because we've got quite a lot of crowning on this. In this particular example, we could probably do a better job of that by optimizing that, and we have the capability to do that. But this is part of the way of checking how as well as looking at the noise, how this affects the durability. Here we're looking at the stress on the tooth surface. We can also look on the gear tooth to see where the contact's occurring in a more realistic way, and this allows us to compare these kind of results with contact pattern tests that you may do under testing conditions. But we're primarily interested in gear whine and the transmission error, so I just need to let the software know that this TE that I've calculated, I wanted to use it for the subsequent dynamic simulation. So that's done that. We've got our TE, and we can now go and run this analysis. We'll look at our fifth speed low case and run our dynamic simulation. So now we're looking at, not looking at the statics anymore, we're looking at the dynamics, we're analyzing the vibration. For those of you that are into these things, this is a eigenvalue solution, and it's producing a frequency domain model in terms of natural frequencies and mode shapes. And that's what we're going to excite with our transmission error. So it runs very quickly, as you can see, and we're now in a position to look at some results. So let's go straight in and look at the vibration on the housing. We were looking at final drive gear, so I select my excitation as being our transmission error, first harmonic. We've got some sensor positions set up, accelerometers there, and we're looking at the acceleration at these two particular locations on the transmission. And very, very quickly, because it's a frequency domain method, we can get a prediction of vibration response at those two locations. Of course, we can look at vibration response anywhere on the model. Here, I'm just looking at two specific locations. So those are the kind of things we're going to be comparing with vibration targets. We could look at mount locations and that kind of thing as well. We can also export these vibration results and run them through a acoustic radiation simulation to predict the radiated noise, as you saw in the example that I showed from Ford earlier. Down here we've got listed all the modes, their natural frequencies, and we can also look at their mode shapes. What is of particular interest is which of those modes are the most easily excited, and we have a metric here called modal flexibility that allows us to look at that, and we can pick some of the modes that are most easily excited and see which of those are important. So let's look at the top one on the list. I guess is a good place to start. And we can look at the mode shape. And see if there are any specific issues. So in this case, this model is very lightly constrained. So we've at the interface point, it's representing a particular testing condition. So you can see we've got large amounts of deformation there in that mode. That may not be realistic when it comes to a real situation of this gearbox mounted in a car, but it gives you an idea of the kind of things that we're looking at. You can see these hot spots, and if we felt that these were excessive hot spots, we could look to stiffen up the housing in particular areas to avoid that. We can also see what's going underneath the housing and see how other components in the transmission are contributing to that vibration. So you can see there's bending happening in the shafts here as well that are contributing to that modal behavior. So that's just one example, and obviously there are other two that we don't have time to look at now that allow us to investigate in more detail, allow us to troubleshoot, for example, identify problem areas, so we know not only that we need to go and fix something because our vibration hasn't met it, or noise hasn't met its target, but also give us clues as to what we should be doing in an attempt to do that. But the final drive gear isn't the only gear that's producing noise in this example. In fifth gear, we also have the fifth gear itself. And if we want to look at the effect of multiple excitations all at the same time, then we can do that, and we can plot them all on a waterfall plot, which is the usual way NVH people like to look at this kind of thing. And so we can see here, and we get a little bigger, we can see here all of those. I've selected the first three harmonics of transmission error for both the final drive and the fifth speed gear mesh, and we can see how the response at this particular location, one of these accelerometer locations, is varying both with speed and with frequency, and we can use this to identify where particular orders of the gears interact with particular resonances in the system, leading to problems. We can also see that because the higher harmonic excitations are smaller from the transmission error, then we end up, as we go upwards in order, the responses get lower. So it's these things that are going to be the most important ones. These are the ones that are going to stand out. And again, we would have, in the real world, we would have targets against which to compare these things. So that's a very quick overview of simulating gear whine. We've gone from simulating the static deflections through to getting the misalignments, through to getting the transmission error, through to getting the vibration response and more. So I'm now going to just pop back to the PowerPoint presentation, and we'll just go through a quick summary before we go to the Q&A. So, summarise, here are the key things I want you to take away from today and to bring with you to the next sessions in this series, which I hope you'll be coming to. We know that gear whine is a tonal noise and it's caused by transmission error. We know that transmission error depends mainly on the gear geometry, the applied load, and also critically on the misalignment. And because of that, we need to consider the whole system when we're simulating gear whine and designing for NVH. Also, I said it was very important, you need to consider all performance targets, not just NVH, when you are designing for NVH, because anything that you do to the design to change NVH behavior or design for NVH behavior will also affect things such as durability, manufacturability, etc. We've seen that when we come to look at gear whine, it requires us to consider the dynamics of the complete system again. Again, we're not just looking at the gears and TE. That is an important part, but it's not the whole story. We need to look at the dynamic response of the whole behavior, because that ultimately is where our targets are going to be defined and how we're going to decide whether we have a successful transmission or not. And we've seen how simulating the NVH performance throughout the development process, right at the beginning all the way through to the detailed design, is the key to having a right first time design that gives us a higher quality design, cheaper and faster than we would otherwise be able to do. So that concludes my presentation. We're going to follow on with a Q&A session in just a moment, if you haven't already done so, to ask some questions, and we'll get through as many as we can before our time is up. We'll probably have time for 2 or 3 questions. Okay, so we only have one question in so far, and the question is clearances for manual transmissions. What's the range of clearance bearings for correlation of vibration response? Clearance bearing, for those of you that don't know Romax design, clearance bearings are a way of modelling parts rotating parts that have clearances in them, and they're one of the things that either you need to be able to calculate from tolerances from drawings and CAD, or to be able to and that way. So ideally you should be deriving what your clearances are for those clearance bearings from your CAD geometry and from knowledge of the tolerances that are on that CAD as well, that you get on the drawings. And this is it's actually one of the critical things that affects the vibration. And when we talk about variability, things like clearances have on them. They make a big difference to how vibration is transferred, because a larger clearance requires a larger deflection to be able to close the clearance, and that has a significant effect on the stiffness and the path of the vibration. So my advice is to take it from the nominal design obviously comes from the CAD, but there will also be tolerances associated with it, and to investigate the tolerances and the sensitivity of your simulation to those tolerances. Another good question, is there any calculations with different lubricants? So lubricants are known to, in a general sense, highly viscous lubricants or having more lubricant in a design is known to increase the damping, for example. In our case, as in pretty much any CAE process, damping is something that is very, very hard to predict and is largely determined based on experience or test based information. So specifically in terms of damping, we are not including the effect of lubricant on damping, but you should be able to, from your knowledge of your particular products and the particular lubricants you're using, you should be able to adjust the damping accordingly. All the damping is adjustable within our dynamic model. Okay, we've got time for one more question. Here's a good one. Yeah, this is very interesting actually. How challenging is it to work closely with the durability team and keep up with the design changes at the initial stages and also account for whine noise and feedback from simulation? Yes, it is difficult. And the questioner, the person asking that question seems to be saying that the people who are responsible for durability are different from the people who are responsible for NVH. And that is quite a common situation. The ideal situation is that you have your people who understand durability have a little bit of knowledge about NVH, and your people who are the NVH experts have a little bit of understanding about durability. in terms of what we supply with our software, the software can show you both things at the same time. We can look at things like gear life and bearing life at the same time that we are calculating transmission error. So when we change an element of the design, we can very quickly see that. And you can see how quick these things are to run. It doesn't take long. So if you're designing, optimizing, for example, a gear for NVH and durability and efficiency simultaneously, then we can calculate what those things are. We can define cost functions that allow us to understand the relationship between them. For example, we might want to, obviously we want to minimize the TE, but we want to make sure things like we don't have edge loading of the gear teeth. We want to make sure that we don't have gear contact stresses that are higher than a particular value. And we can do that, and as you can see, it only takes a few seconds to run these things. I'm afraid that's all we've got time for in terms of Q&A. I see there is more questions have come in as I've been talking. We will try and respond to your questions individually during the coming days where we can, but please bear with us while we do that. But we will try and get back to you. So just to finish off, I'd just like to remind you that further questions that you haven't asked today and you'd like more information on, or more information about this topic, then talk to your Romax representative or contact us on this email address here, and we'll get back to you and we'll get somebody talking to you and helping to answer your questions. In a few days' time, this webinar will be available for download on our website if you want to have another look at it. So you'll receive notification of when that happens, and you can come back to our website, have a look again at the kind of things that we've been talking about today, and revisit them, and again, an opportunity to ask more questions then. Just a reminder that the next webinar in this series on practical solution of Gear Whine problems, looking at individual case studies in some detail, my colleague Adam Austin will be presenting that, and that's on the 7th of July, and then we'll be looking at in detail at sideband, planetary gear Whine, and particular planetary gear sidebands the following week. And again, I'll be back presenting that, and we'll follow up a few weeks after that with a final session, which is on electric machines and electric drive lines. So thank you very much for attending. We've had a very good attendance both this afternoon, our time, and also in the earlier session today, the highest attendance we've ever had for a Romax webinar. So thank you very much for your interest and attendance. I hope you found it useful, and I look forward to discussing some of these things with you in the near future.